As I was trying to figure out what the title for the talk was, I was wondering how many people in the audience would already be familiar with the term impedance matching. If you heard of it, raise your hand. Yeah, I figured a lot of people would be, particularly in hardware chip design. Some people in chip design or more RTL level may not know about it. I wasn't sure. So why do I use the term impedance matching in this case? So open hardware, as I refer to it, refers not just to the world of silicon and RTL, but I'm referring to like system level and the larger phenomenon of people pushing for more transparency in the gadgets that we have. And the arrival of open silicon is going to be a massive paradigm shift for open hardware and the people who are building these systems. And the problem is that change is going to come faster than the user base can actually understand the issues with open silicon. And by definition, if the rise time is faster than your propagation time, you're in a transmission line situation. And if the load isn't well matched to the energy that's coming in, you can actually risk getting reflections, or actually like the energy being lost upon the community if the sort of the energy coming from the open silicon community isn't well matched into the expectations of the open hardware community. So just a quick review before I get into it. Why is open hardware happening now? This is a slide that everyone's seen over and over again. This is clock speed over time. This is just a compilation of clock speeds of Intel CPUs over time. And you're familiar with the Moore's Law curve, and there's like little bump that happened in the mid-90s, and then this little the Pentium 4 crown, and then like things have just been flat for the last decade or so in terms of clock speed. So Moore's Law is dead. But what does that mean in terms of like what individuals can do? And a lot of times openness and the idea of doing projects on your own and sharing source code is about small groups of people doing things and improving things in an incremental fashion over time. So if you take this graph here, this is a log plot, and the straight lines would be different trajectories of Moore's Law. So if this Moore's Law once every 18 months, how much better does something get on a sort of arbitrary unit scale, right? So this is the most aggressive curves, 18 months, 24 months, and 36 months. And then there's this curve line here, which represents, like, if you were just to take a baseline system and say, spend a year, optimizing your assembly or doing a little parallelism, maybe get 75% better. And then the next year, you spend a little more time, you get 75% better. But it's not compounding on itself. It's an incremental improvement, so that's within a particular node. What you find is that, if Moore's Law is moving at a rate of once every 18 months, which it was for a while, essentially by the time you finish your project, you might as well throw it away because there's a faster computer out there. And that's the realm that we had been in. Back in particular in this region here was particularly painful for people trying to do system-level architectural improvements. Now the scenario we're in right now is like, t equals 24 to t equals 36. And we can see is actually people who are working within a given process node or working within a given system have a much larger window, actually measured on the order of like years now, to go ahead and make improvements and have them actually still be relevant and not have something costing $99 blowing them out of the water at the end of the day. And so you have more time at a given node to refine your ideas and to create systems and create platforms around it. This slide is a slide that I shamelessly stole from an NVIDIA presentation a while ago and was used inside an article by E-Times that was claiming 28 nanometer is the last node of Moore's Law or whatever it is. And the argument they were using was that, yes, there's like this sort of slowing trend in terms of the introduction time, but also there's this upward push in terms of the actual cost of wafers over time. So this is a 80 nanometer, 55, 40, 28, 20, 14. Those are the wafer costs at a given node. And so what you saw before is there was, if you were in one node, there was a strong incentive to hop between wafer nodes just cost-wise. If it wasn't even performance, you would go to a die shrink to move your process ahead. Now what you're seeing is even though the new wafers are becoming available, there's not as much an incentive to even move to the faster, to the smaller die shrinks because the cost incentive isn't there. Your performance is fine, then you're just not going to move ahead. And so there's this double whammy in terms of like maybe Moore's Law is continuing to tick along every 2 or 3 years, but people are just not migrating to the smaller nodes. What this leads to is an interesting sort of case study that happened back a few years back. It's a project that I did with Sean Cross over there in the audience. Raise your hand, say hi. Yeah, him and me decided one day that we were going to build our own laptop. And we said, build our own laptop, obviously not through the silicon, but like from the circuit boards, the plastics, everything. Like, it was time. We wanted to build something that we just could call our own, and it had all our own weird features and specs. And so we ended up designing this motherboard here, which is based on an IMX6 CPU sock. It's a Cortex-A9, and it has like weird features like 2 Ethernet ports built in. It has an FPGA on board, and it has like the video interfaces is actually a card, so you can talk to multiple different LCD panels, and a bunch of other kind of weird things. But if you were to build a laptop just for itself, you would put those features in there. And the really interesting, and so eventually what happened was when we got to the point of wanting to go to tooling, we needed to raise a certain amount of money to do it, so we went to crowdfunding, put it out there, wanted to sort of recover cost of tooling at $250,000, managed to hit $750,000, and the numbers aren't actually interesting from a volume perspective in terms of silicon. Normally, I mean, this would be a total failure if you're Lenovo and you're only doing $750,000 sales in laptop. But it's interesting from the perspective that essentially there is a market of people who are willing to pay $2,000 for an underperforming laptop with really weird specs. So if you could just maybe build something that had some reasonable performance numbers and some normal specs, there's a premium market available for people who want openness in their hardware. And we'll talk about that a little bit more. But the main point of sharing this is that there's a new reality that's happening now, is that you can take 30 months to go from a concept to delivery. So if you overlay on this sort of Moore's Law curve, here's the process nodes going along. If here's a 40 nanometer curve, the IMX6 was fabbed in sort of early 2011. And the chip was out there. It's not like we were working with the fab before it came out. We're like, okay, we're getting full production silicon, and we're like, let's think about building this for like a year. And then go ahead and launch it, deliver it, and there's this window, this pink window is like sort of where we could monetize it. And then finally we hit obsolescence, where it kind of declares when the Pi 3 came out with a quad-core 1.2 gigahertz CPU at $35. There's really no point in getting Novena at that point in time. You just drop a Raspberry Pi inside. And the interesting thing is when you overlay this graph, sort of the post-Moore world versus the previous 30 years of innovation as industry has known it, in order to stay on this treadmill, you basically conceived your system-level project almost at the same time the silicon vendors were planning to do the fab. And then the fab would happen, and almost the same day you want to be launching your products and trying to ship them out the door. You have a very short window in which you can ship them. And if you don't deliver within a year, you're already obsolete before the market has happened. And so there's this change, essentially, just even a small shift in sort of the Moore's Law slowing down and the nodes sort of pushing out, creates a lot of breathing room for small groups of people, small system designers, to try and create systems of a greater complexity than seen before. So this is why you're starting to see ever more kind of relevant open hardware concepts being pushed by the community at this point in time, because we actually have the time to work on it and the time to bring it to market. So when I say open hardware, I'm putting air quotes around it, because what is kind of open hardware? From our definition, we shared with people the 3D design files for everything, from the circuit board to the cases to the tooling for the injection moldings and the CNC. We shared with them the circuit boards in a binary format that's editable, as well as in Gerbers, and also the schematics in a binary format, as well as in PDF. But if you were to ask, as many people what open hardware is, you're going to get as many answers today. There's a lot of contention among the community itself over what open hardware is. And several years ago, there was like this big mailing list of people who got together and said we should probably define what this is and come up with a logo and try to protect it, blah, 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 big working group kind of thing. And they finally came up with this statement of principles and a definition. You can go to oshwa.org/definition and read it. Instead of making you read all the little text, I'm going to unpack sort of what was sort of like the mission statement a bit, which is where I think really it's more about the intent than necessarily the strict definition of things. So open source hardware is hardware where it has been open so that you can study, modify, distribute. So those are pretty easy ones. I think everyone gets that. But then there was a bit of argument over this, over like the terms that you also must be allowed to make, design, and sell that hardware. There's a group of people originally who wanted non-commercial licenses, which don't make any sense at all in open hardware. It's not like Software, where if it's non-commercial, you can get a copy and run it and still do something useful with it. Hardware, me giving you the plans doesn't allow you to progress the state of the art at all. So one of the things that we agreed as a group is in essence, anything that's open hardware, when you put it out there, someone else is allowed to actually use your plans and perhaps even compete with you as a visual manufacturer. And we consider that just sort of fair play in that community. This line here was very contentious. How do we share the source? You know, the language we ended up choosing was available in the preferred format for making modifications to it. So if I gave you a circuit board in Gerber's, or I gave you a chip design in GDS2, it's not terribly useful for making modifications, but I've allowed you to manufacture it at the end of the day. On the other hand, if I gave you a file that's openable in Cadence, you're going to need a $1 million license to open and edit that file. Or if I gave you a file in Altium, it's a $5,000 license to open a circuit board design. However, that's what a lot of people would edit their stuff. And so there's one half of the community was like, it's not open unless you use open tools, which means that we're all now back to designing chips and Magic and circuit boards and like FreeCAD or whatever it is. And that would really greatly limit the amount of open hardware that's out there. And so we sort of came up with the language of like available in the preferred format for making modifications. That's deliberately from the eye of the beholder and the person who would do it. So basically, if you were to make more changes to it, how would you like it? And as a general courtesy, as a sort of a nod to the community, you would release a PDF form or like a Gerber form or a GDS2 form. It's like so people who don't have the fancy stuff can at least kind of study and learn from it, but maybe not necessarily create a derivative work of it. Another one is that, and this one gets even more contentious when you get into open silicon. Ideally uses readily available components and materials, standard processes, open infrastructure, unrestricted content, and open source design tools. That doesn't even, I don't think it has a mapping into open silicon. You know, what are the standard, well, there's not kind of standard fabs, right? But are those things even open? You know, there could be an argument that you have to use only Moses SCMOS rules or something because those are the, you know, the most free PDKs, and that's not gonna cut it. In terms of like the readily available components materials clause was put in was because some people were labeling hardware as open, but then designing these modules in that were basically unobtainable through a single source and trying to push a standard on the community by you know, as a kind of a Trojan horse. And so they wanted to sort of be able to call those people out and say that's not actually open hardware by just sticking your black box on the PCB and sharing that spec was not good enough. But this will be educating a community of people who don't understand any of the issues on chip design and how this maps into their preferred definition will be an interesting challenge for I think, you know, the open silicon community. And then this final line is, I think one of the kind of the punchline of it is that essentially what people want at the end of the day is freedom to control their technology while sharing knowledge and encouraging commerce, right? So the freedom to control your technology and not be controlled by it is a recurring theme we'll see through this talk, and the ability to share knowledge. So a little bit about what it means in practice. This is an example of an open hardware design that happened just actually after the big earthquake in Japan and the reactor blew up, Fukushima blew up. A group of citizen scientists self-organized called SafeCast and built a Geiger counter that you could go online and you could buy from parts. They released the circuit board, you know, circuit board designs as they were. There was a bunch of modules you can see, like it's a little hard to read on the screen, but this is the GPS. It's a rectangle box which has like 3 volts in and ground, TX and RX. I mean, is that open hardware or not? Okay, well, let's have a look at it. GPS module is this thing from Adafruit. Adafruit's a great open hardware vendor. Let's look at the module. You can tell from the module itself, there's like this thing. Is that open hardware, or is it good enough that this is at the board level is open hardware? Well, you can go to the Adafruit site, pull down the schematics, and sure enough, you can see it uses a micro regulator, and then there's this MediaTek chip on the inside that essentially does everything for the GPS and the antenna and whatnot. You go to the Adafruit website and say, okay, well, I want to learn more about this stuff. Oh, that's good. Like they have the command set for download, and they have like the data sheet for download, and they have the CAD files. Looks like they're checking all the boxes, right? Except you go and click on the link, and this is what you get. You get this thing that says Global Top Confidential printed right across. I mean, just the direct link, you know, is to this thing, which clearly does not have the correct licenses on it, but is being shared anyways. And then they have like still the copyright notices that, you know, this is being served off the Adafruit CDN site, and it says like, Document exclusive property of global text should not be distributed, reproduced in any format without permission of global top tech. I mean, and this is where you sort of like run into sort of like this standoff that the community now has with hardware vendors, particularly the silicon vendors. The silicon vendors want you to buy their silicon. But if everyone has to sign an NDA to even start designing with it, how do people even begin to start designing with it? And so there's a sort of like wink, wink, nudge, nudge, like, yeah, you know, the leaks happen and we sort of turn the other way. And then you say, okay, well, this is great. This is actually still system level stuff. I want to learn more about what's inside the chip. Can I look up the chip spec sheets? And Adafruit doesn't link to it, but sure enough, Baidu has a copy of the MediaTek, you know, data sheet here, you know, with, you know, confidential, whatever, like watermarks all over it and nonsense like that. And then now you're sort of entering the, you know, the wonderful world of sort of Shanzai practices and, you know, sort of the dark IP network that exists here in China, which is also very fascinating and a completely different talk in itself. But there's a whole set of practices that a different community has adopted to deal with this gray zone between what the chip industry does and what we need at system level to get hardware produced. Now the thing is that, you know, open source is now it's turning into more of a marketing term, so people are starting to apply it to more and more products. So shortly after the Novena Laptop was out, another laptop called Leoben, the name in itself is meant to invoke freedom and, you know, libre. Introduced a laptop that respects your right. They raised $500,000. They did 2 models, so actually the total raise was $2 million altogether, and the price points weren't low either at the end of the day. And these guys were very unabashed about creating marketing slides. You know, they had like philosophy slides. Purism will only use free, libre, and open source software in the kernel OS and software. They'll design and manufacture hardware that respects your rights. They're going to prioritize privacy, security, and freedom. They're not going to discriminate people, and they only source and manufacture the highest quality hardware. And they have this like really kind of interesting, you know, very marketing kind of, you know, table of everyone's no on BIOS-free, kernel-free, promotes freedom, like in the names across the side, like Microsoft and Dell and Fujitsu. And hey, look, Leoben's like the only one that can actually hit all these points. But the thing is that there's a group of people who this actually really appeals to. It's a minority market, but they really, really care about it. So even though I sort of kind of jab at it a little bit and how much they're pandering to that market, the fact is that there is a market that cares about that, and they care deeply about that. And one of my favorite slides from their set is this graphic they compiled of each of these little boxes of a software program that you could run on Leoben. And if they're green, they're open. You can like download all the source code for it. And so this is your software stack. This is the GNU OS. And then there's the free kernel. And then there's the bootloader. And then there's the hardware BIOS. And there's 5 little boxes on the bottom. The component firmware and the hardware kind of level stuff. They were counting, including like the microcode you could upload into the Intel CPU. And so this is almost like a big arrow pointing down at the impending problem that these guys are facing as they want to get more open, is that the trust roots are always closed still, because they're inside the silicon and the vendors don't want to share that information with you. And this sort of like gradual sort of becoming aware of the fact that like there are lines of code that we can't control inside systems that we want to trust and we think that we have transparency into, is stoking sort of demand for transparency, right? And there's a bunch of conspiracy theories, and you have like sensationalist headlines like, is the Intel management engine a backdoor? You know, expert says NSA have backdoors built into Intel and AMD processors, or like, you know, this headline I love, Intel's management engine security through security should scare the shit out of you, right? And it's just like, people like, and the thing is you know, they're clickbaity, but at the same time, there's a granule of truth to it, and it's driving sort of, you know, a mania amongst people to try and solve this problem. The result at the end of the day is actually, so now what you see is as people become more educated on the issues, there's a higher standard for transparency being applied to what are computers versus IoT devices. So on the IoT devices, we were okay to get away with the GPS module example, going down to the confidential MediaTek data sheets that you could download. And this is an example of a conversation I had with Richard Stallman over the Novena Laptop in December 2012. He shoots me an email over here where he says, like, I read about your plans for an open laptop. Unfortunately, it seems not to be so. The GPU, which is in the same chip as the CPU, can't be removed, requires a firmware blob, and therefore the program is not free software, not open source either. So this is his like opening remarks to me about this, right? Dozens of emails later, and this goes on until like April 2014, and we even discussed them of building a custom version of the laptop that has the GPU fused out, because Freescale has a SKU where it eliminates the GPU and so on and so forth. But they don't have a version that fuses out the VPU as well, which also requires a blob. We were never able to actually get certified under Stallman's criteria for respect to freedom because we couldn't eliminate the video coprocessor. And his fear in particular was that, you know, a machine that includes a piece of hardware, even though it boots, you don't have to load a blob, but it's just there waiting, is like the siren's call to get people to use non-free software, right? And so he was unwilling to go ahead and certify the system because we still had elements that could run blobs, and the only way to run them were blobs. And his intermediate sort of come out was like, you know, I'll help you reverse engineer this so we can have free software to run on it. But, you know, until then, I'm not going to go ahead and certify this. And, you know, he's genuine. He's actually referred to me multiple people who want to reverse engineer this, and we actually raised extra money in our campaign and spent a bunch to try and get the GPU reverse engineers and also, but it's really hard to reverse engineer a GPU and VPU from scratch. And so there's been this sort of like, you know, standoff here. And this is just at the GPU and VPU level. Like, I dared not really get into the subject of the boot ROM inside the IMX6 or the fuses or the trust zone or the fact that my SSD had a firmware. Like, there's all this stuff that I knew that was in there, but, you know, we just started walking this path and we got kind of to a point where I couldn't handle it anymore, just talking about GPUs and VPUs. And so this is sort of a preview of what kind of standard transparency I think lies ahead for people who want to market open silicon, particularly to people who want to do computing. And so from the software stack side, they think their requests are very reasonable because to them transparency is easy, right? I mean, this stack here, the width of it shows the relative difficulty someone in software might encounter to obtain the source files. And it's basically it's the same width. It's easy and common to download source files for browsers and VMs, servers, compilers, tool chains, OSs. And then you start to sort of touch on drivers and BIOSes. It gets a little bit uncomfortable, but at least you have options there, right? You can sort of choose to use a network chip that's maybe a little bit older, but it certainly lets you get your work done and you're okay with it. And so as they start pushing down this chain, I think the software people have this expectation it's straight all the way down. But when you get into silicon, you have quite a different situation. That the difficulty gets exponentially harder the further you go down that stack. So at the very top from the silicon, there's the bus interfaces. Okay, people give that away for free. People want you to plug in a PCI, and people want you to plug in USB. Modules, you can usually at least get the module vendor pin out from the module vendors. PCBA, we're just starting to become aware of the issues, and that's starting to become a popular thing to share circuit board designs. And now, here at this conference, we're now looking at opening up chip designs, right? And so, but then people need to be educated. You know, the word PDK has no meaning. If you said this at, like, you know, Linux conference or something, you said, oh, the PDK is not open. They wouldn't know what the P and D and the K mean, or even what it means at the end of the day. And he talked about foundries, and they've heard of the names of foundries, but to them it might as well be Disneyland, right? You know, because people wear suits and they dance around inside fabs, according to the marketing slides. And then you know, you get in further and say, okay, well maybe you managed to open all this sort of stuff, and people go like, but wait, I mean, there's this machine that puts my ROM pattern on here, a stepper. Do I trust the stepper? Can I get the source code for the stepper? You know, and can I see, like, can I inspect the stepper itself to make sure that's trustable? And then, oh, where are the raw materials coming from, and so on and so forth. You get all the way down where essentially you get to, like, impossible barriers for transparency, and these things are actually all essentially in your supply chain, right, at the end of the day, if you're trying to build trust roots. And so there's actually an impenetrable barrier, a layer at which you just can't get any further on, and that's one of the sort of impedance mismatches that the software guys, you know, they have all this sort of momentum pushing them down this way, you know, going towards the open thing, and they're going to hit an open circuit at the end of the day. and that energy is just going to have to bounce back at them, and they have to figure out what to do with it. But ideally, we can sort of ease that transition a bit. What sort of further aggravates this issue is that this here is a graph that sort of shows the awareness that people have of the trust issues that they're going to be facing. And so the width of this bar is roughly proportional to their awareness, is a rough indicator. And the point is that okay, at the BIOS level, a lot of people are aware that, okay, BIOSes are a problem, they should be open. And then there's a large but only slightly smaller set of people who are aware that there are firmwares in their SSD or their GPU or their boot microcard. And then, like, basically almost no one's aware of the fact that silicon ships all the time with extra blocks that aren't even documented or turned on because maybe you put something in your sock, it didn't work, you fused it out. And people, if you were to then, I could just see the paper now, like, oh, like, NVIDIA shipped this chip and they claim this stuff, but there's this whole section of silicon that no one talked about. What's it doing? It's hooked up to all the buses, it's sniffing all our things out, like all these conspiracy theories start coming out. And then all the chip guys go like, well, that was obviously just a block that didn't work, we just fused it out at the beginning, that's fine. But they're not even aware that this is an issue. And then there's like, code that runs before your reset vector, almost all the time on these socks. And that's, when they find out about that, their heads are gonna explode, because that's like ring -10. And then there's the IP practices, of the industries. You get hard blocks and encrypted netless, and that's what you have to do. And then unfortunately, there's this like expansion of awareness around like mask trojans and glitches. Like, these sort of like, what if someone edits my mask? Or what if someone glitches my clock and gets my CPU doing? So this is like kind of, because it's relatively easy to understand the idea that someone can go ahead and edit a mask, but the other things in the middle are not as clear to them. And so there's a knowledge and expectation gap where, open silicon has the opportunity to sort of push down the stack, but where everyone's sort of looking at is already down here at sort of like the end goal at the end of the day. So there's a burden that open silicon vendors bear to educate the system level decision makers. Like, first, they need to know what are the realistic and imminent threats to their systems. If the threat model actually isn't calibrated correctly. Then you need to tell them how you're addressing these issues, and then you also need to talk about what are the practical economic factors that limit transparency. And you're going to get a lot of pushback on it, because I've already gotten people saying like, oh, well, what if we start a foundation to create our own fab? Can we just like buy out an old 8-inch wafer fab and just run it and do open silicon in it or something? Like, questions like this have come up, and some people with some serious money from some Silicon Valley communities say, oh, well, we can fund this. And it's like, yeah, the problems are harder than you think. So just as a thought experiment on the limits of transparency in silicon, after Novena and sort of my experience of not getting the laptop certified to the level the community was satisfied, I was like, well, can we build even like an 8-bit CPU that meets the standard that they want? And so I was inspired by this project called the Visual 6502. There's like this, you can go to a web page, and a bunch of guys went and they took pictures of the 6502 mask layer by layer, drew geometry around it, and do a transistor level simulation in JavaScript of a 6502 real time in your browser, right? So this thing's great because it's like, I mean, it's obviously not an analog level, it's a digital level simulation of the 6502. But if you can do this, I'm like, okay, we should be able to build at least, an 8-bit chip using Magic and X circuit, or whatever Yosys, Q router, design flow, pick an SCMOS rule, from MOSIS that, where the PDK is essentially an open PDK, and build a quote-unquote totally inspectable trust root. Just a few bits of execution so I can have something I can trust. The problem at the end of the day is I couldn't find any open source IP for storing the code, right? And so I could do all this effort to try and build an inspectable chip, but I can't actually confirm to you your code is being stored where you said it is. I would give them all the GDS2, and there'll be this gaping hole, and they would be like, what's that? Well, that's where your code goes. Totally inspectable, right? I mean, it wouldn't have worked at all at the end of the day, and that's why we didn't move ahead in the project. The thing is that this lack of transparency is endemic in the IP industry, and there are really solid reasons, as you guys all know, for it, is that the fab industry is highly competitive. PDK elements like RAMs and flash and DRAM are very valuable. They take billions of dollars to develop, but they're really easy to copy, right? The moment someone ships a chip out, the first thing someone does is send a chipworks, and they measure all the gate dimensions and the thickness and and the sort of process layers, and people learn from these things very quickly and improve their processes. You know, high-speed mixed signal designs like PLLs and CDRs and PHYs, very hard to engineer, takes a lot of cost to get them right, also hard to protect. And then, you know, even spec-compliant IP, like you do a PCI Express core that's, you know, bulletproof, and a USB core that's bulletproof, and you've spent, or an ISA, right? You've spent years and years getting this thing to be spec-compliant, and someone can copy it by just sucking over the Verilog file and compiling it, right? And so because the development barriers are measured in like literally millions to billions of dollars for these developments, the industry has sort of really solidified a lot of practices I think that'll be very difficult to reform or are unrealistic. And I think the problem is that explaining these monetary barriers to people who have also created, you know, for example, the internet, search, you know, self-driving cars and artificial intelligence and, you know, Alexa, whatever it is, they've all created these things over open infrastructures, right? So their feeling is that we've built fantastically complex things that the world runs on, and we've done it with all open IP. And then they go to the silicon guys and say, like, I don't understand why you guys can't do the same for us, because we've shared everything down there. So there needs to be some amount of education that has to happen there. But this leads to sort of like the security nightmare that these people will have when they learn about this, which is, what if key IP providers are compelled to put backdoors in IP blocks? You know, what if a three-letter agency went to Synopsys and says, you know, put this backdoor inside your PCI Express block or your USB cores. It's opaque, it's RTL anyways, you know, or encrypted netlist, whatever. No one will find it, or Trust Zone or the CPU ISA. That's kind of the conspiracy side. But you know, realistically, the things that people need to worry about are just benign escapes, benign test escapes, which put together as a system create a hardware security breach. So you know, Trust Zone, for example, makes some very big assumptions about having the memory subsystem being intact. And so if anything along the path, say a crossbar switch or a DDR controller has a test escape that allows you to suppress a write or allows you to go ahead and you know, swap the order of bits, which is actually pretty common for like DDR buses. You want to be able to swap the bits around, and it's not a documented feature and you haven't locked that down, then all of a sudden you have a big problem in the wild, which is a pretty powerful rootkit that you can install on almost any device. And so the question is, how do you turn these sort of realistic and conspiracy fears into an opportunity for the RISC-V community? So I think the compromise might be that good fences can make better neighbors. So one of the key benefits of open hardware is the ability to understand everything inside the hardware, but as I said, we can't show all the pieces that we want to ship. And so if we can actually add hardware introspection blocks, things that we build and control within our RTL that can monitor the IP that we're putting into things, that may be a workable compromise. So for example, a thing that I would love to have is like a hardware assert. Assert is a thing you put in a line of code that says that if this condition is not met, throw an exception, so you can go ahead and catch a program that's behaving buggily. And so I saw earlier in the workshop that you guys are talking about a PNP, which I love. That's a great thing that you should have. But that protects user processes. That's a processor emitting a write to the wrong place. However, you have third-party IP. Those things can also emit writes that go to the wrong place. So you want to have essentially something similar to a PNP, but for third-party hardware IP. You can wrap around it that can log or trigger on certain transactions. And ideally, you would use something like a TAP or BIS to configure it, because if you're relying on all this other infrastructure to confirm that this assert block is working well, then you could have other exploits there. You want something that's very simple, like a serial scan chain or something to check on that. And the main thing this protects against are things like extra and undocumented registers inside IP blocks, and IP blocks that can be programmed to originate DMA requests to blast pieces of memory. Another thing is that you want to do some storage validation. In terms of mask editing attacks, there are some that are reasonably realistic. For example, mask ROMs are by definition made to be editable. And if you put your trust root inside a mask ROM, you want to have some guarantee that that was the trust root you put in there. It's maybe hard to do. Or there's been other papers like on reset, you can go ahead and trim out like the width of a N or P FET to try and bias on reset or whatever it is. So it'd be nice to have a similar sort of way to just read out these blocks using a very simple mechanism that, sure, I've got a black box ROM, But I can go ahead and just confirm that ROM has what I thought I put in there. And ideally you would do it at speed, at voltage. So it's not like you can have a ROM block that says, oh, I'm being clocked at lower than normal, I'm in BIS mode, let me go ahead and swap out some bits or something like that. You just run it at speed, and you go ahead and you can confirm that those blocks have the code that you thought that would be on the inside. And then, there's the question of IC inspection. These guys are ultimately going to be like, well, it's open, so can't I look at the masks, right? And there's a temptation, in the industry to be like, that is so hard. Like, don't even bother trying. Have you ever even tried to look at 22 nanometer on a SCM? It's like you need the top line SCM and a ton of patience even to get that to resolve. The problem is the patterns that security people have been told their entire life that it's too hard to break that, don't bother breaking it. And then they go ahead and they break it. That's what they do, right? And so, if RISC-V kind of took the opinion that, don't even bother doing it, then you're basically waving a red flag in front of the bull and they're going to charge at you and try to take you out. Usually, the better solution to this is try and find a way to make it their problem to solve. You don't have an obligation to do the checking for them, but you need to give them enough information so they can try the checking themselves. And if it's really hard and they draw the conclusion inside the community that's hard, then okay, fine, it's not your fault. But you don't need to be there trying to convince them. The problem is that there's a lot of process-specific details, even in the metal masks, like phase shift techniques and tiling and whatnot. But as a compromise, it may be possible to do mask inspection without having to give up PDK details. What these guys really need is they don't need a satellite photo of a chip. They don't need to know about the actual GDS2 layers. They need an abstract representation of where you intended the metal wires to go. So if you gave them a list of centroids of where the lines should be, and they can just go ahead and run some image processing algorithm and confirm that those centroids are where they need to be, that'll be good enough for them, I think. And then there's sort of an issue. So here, then there's an issue of also a lot of founders don't want to share the lower level masks, for example, the transistors or the low metal layers. And I have maybe a compromise is you just give them metal 2 or metal 3 and up, right? And you have outlines for where the standard cell library should be. And you say, okay, trust me, these blocks, this should be a NAND gate, this should be inverter, this should be a spare cell or wherever it is, these sorts of things. And while you could do a transformation of, say, an AND gate into a NAND gate by just shorting out the output inverter or wherever it is and shifting the logic, what this really prevents is that if someone were to modify your RTL from what you compiled to inject a multiplexer, like a full multiplexer and a backup ROM to go ahead and show you a different piece of code, you're not going to hide that with mods metal 2 and down. You're going to have to do mods metal 3 and up to do that sort of stuff. So there's a bunch of very gross functional things you can guarantee about your RTL from metal 3 and up. And the hypothesis is that metal 3 and up is less protected IP, and so you can go ahead and push that out there. And then it may be possible for security critical blocks to have some RTL structural and synthesis techniques that harden it against the possibility of standard cells being modified. So if you had multiple redundant paths for computation, some parity checking, a bunch of other things, so you had, instead of just swapping one cell, you had to swap a set of cells in a way that would be difficult. You can probably build something that at least makes it very, fun for someone to go ahead and make that change. And then, the community itself would then figure out some way to randomly sample and the introspection blocks. So ideally what you would do is, when I was talking about the harder fences and sort of the BIS tap readout, you would have like this empty block in your GDS2 with a bunch of metal pins, and then you would have this little area here, slightly isolated with the introspection block, and maybe a couple little alignment features. And then this would assist the guys who are doing the readouts, says, yep, we're just going to look here and confirm that the thing we're using to check these blocks is not modified. And if we can confirm that's good, we can trust everything to the right of this block over here. And so you would kind of design this for inspectability, and then they can go ahead and do some sort of random sampling to make sure that the root of trust is there. And that would be a way to sort of, I think, strike a compromise with that community. And again, the onus isn't upon the designers to have to do the validation. You just need to give them the ability to do it the best that you can within economic limits, and you can fair enough charge them for this as well. If they want this as a feature and it takes extra silicon, it's going to cost you more money, blah, 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 all this sort of stuff, and they probably would pay for it. So as a recap of sort of maybe a compromise position, assuming that you're willing to be 100% open on your self-generated RTL, and this includes being, disclosing things like pre-boot config and fusing and other techniques that you may have. And you don't have to do that. Obviously, RISC-V is a very permissive license, so there's some closed designs as well. But if you're trying to get into the open hardware market and the trustability, there's some ideas that you can use to try and work around the IP transparency issues of the silicon industry. They include things like assert blocks, kind of a PMP for the third-party IP, some open tap verification of black box memory devices, and like a street map of high-level metal, and some assistance for the mask readout ability. Now, in terms of what can happen if your impedance is mismatches, you do run a risk that things can backfire. So I'm a big fan of what Sci-Fi is doing for open hardware, and they had a campaign recently and it supported it. But I had some worries that some of the expansive claims that they had in their campaign can draw criticism from the open hardware community. And so I'm just going to highlight those here as just like, I'm probably the friendliest messenger you'll ever get about these issues. Someone else from the open hardware community would be a lot less politically correct about this sort of thing. So this is sort of like the thing from their campaign. It says, we have open source RTL. The FE310 is our first open source RISC soft available industry. They've contributed the RTL code to the open source community. You can look inside the chip and completely understand how the hardware works. And so some of the mismatches is like the phrase, see what's inside the chip and completely understand the hardware works. So the first, I saw that, and I went to the GitHub link and I cloned the repo. And first thing I did is I started grepping for FE310 or the word 310 or doing XR grep, but I couldn't find it. Apparently what was pushed didn't actually have the FE310 in it. It had the E300 dev kit and the U500 in it, which is, okay, this happens sometimes, but eventually we'll expect that stuff to get pushed. And then I was like, okay, well, I want to see the ROMs. I want to find the trust root. So I started looking for fuse blocks and stuff like glitching attacks and PLs. And unfortunately, the two very interesting black boxes from the security standpoint are the two very black boxes that exist inside the E310. And so that sort of already creates an impedance mismatch between the reflex impulse that someone like me has looking at this versus what's actually delivered. And while you guys have made huge strides in terms of openness, that initial sort of disappointment and not finding the things I'm looking for makes me go, like this is not going to get us there. So I think it's better to be explicit and clear. You're talking to an educated audience. They understand diagrams. And so it'd be nice if you just sort of took some of your, you have this diagram published on your website and just said, everything in white here you can inspect, right, at the RTL level. But there's these blocks here on the right-hand side which, for various reasons, we can't share with you their vendor IP. And I don't know if, in fact, this is closed or not, but I didn't find that in the code base. So I said, look, maybe it's closed, who knows? And then, if you can then add fences around it and say, like, look, we actually have like these little bisque fences around the outside of these blocks that we can't necessarily show it to you, but we've neatly sort of cordoned off to a section. You can actually check that these things aren't doing something wrong. You can confirm that your mask ROMs actually have the right code on the inside. That may be a more than sufficient compromise to get you to like pretty much an unparalleled level of trustability at the silicon level and what these people care about. So what I'm saying at the end of the day is you really just want to spell it out when you talk about open silicon to non-silicon diviners. This is again like one of those marketing charts, but like, everyone else may have an open BIOS, but like no one else has like, their firmwares or the boot microcodes available. No one else tells you about the hidden infused silicon blocks. No one even discloses the fact they have pre-boot microcode. IP industry practices, okay, what are you going to do? But we have a workaround to sort of like fence in the guys who are a problem, and depending upon how much you want to bash your head against the foundries, you may be able to address sort of the mass Trojan and glitches issue. The upshot is that if you were to go for a security or trust group target market, right? That's a very high value segment because people obviously they want small, low power chips, but they're being used to protect secrets of very high value, right? So you don't, if you say, yes, I could buy a $1 microcontroller, but maybe you would spend $10 to get something that can secure your $100,000 bank account or your, the keys to your DNS server or whatever it is, that sort of thing. You can charge a lot of money for it. And it's also a very protectable advantage relative to the rest of industry. Like if you start to say this is the standard for someone to be a trust root, they have to be this open, and this is what the sort of the community has accepted. then guys who are trying to sell trust roots like ST and those guys, they can't compete because they won't be able to meet that level of openness. You're going to have essentially very little competition from the incumbents around the transparency place. So it's a protectable niche that you can get into. And the other thing is that even though the standards for scrutiny are higher, you may be able to push those costs onto the user. For example, the back-end metal inspection, that sort of, if you're clever about it, you can actually set up a service that you make margin on, saying like, look, if you really want to have like a sampling service, pay us a subscription fee. We'll, you'll have an audible lab. You can go ahead and we'll give you a certification, and we can check that these chips are doing the right thing on a constant basis. So there's actually, the point is that the security trust root model, there are people paid a lot of money to secure very high-value secrets. So I think there's a market there, but you have to be able to approach it the right way and be very transparent about your disclosures, and not just try to make broad statements about what this is without necessarily being able to back it up. The other half of the market that I think that might be out there, sorry, these guys are sort of just the open source and Libre movement zealots. There's a bunch of people there who really care about getting premium laptops and servers that are just ROF, respect your freedom certified. And this is a more basic certification. You have no blobs and you promote user freedoms. But the thing is that, and the good news here is that your scrutiny will be proportional to your security claims. These guys probably won't care about the back end sort of verification, and they may not need as much level of scrutiny over the hardware inspection, but they probably want some of it. On the other hand, they're going to have a higher I/O and higher performance requirement. And so one of the things actually that was asked of me was to try and come up with an idea of what would like a laptop look like, or sort of a CPU look like for a laptop for this segment. And I started putting together this slide. It was like all the things you expect, like lots and lots of fast wide ECC memory, more than 64 gigs. You want to be able to run your hypervisors and have some basic core extensions, all sorts of stuff you see. But I realized this was kind of going off into the weeds. Really, the point at the end of the day is that you don't want to necessarily integrate so much IP into the system. Like for example, an integrated GPU would be a minus to that crowd because probably the drivers would be closed. Instead of even worrying about a GPU IP, just go ahead and get a fast wide PCI Express bus and use a discrete GPU. And yes, that's more expensive, but that's the sort of thing these guys would pay for. Instead of trying to pull in like SATA IP or like Ethernet IP or what these closed blocks might be, just put down a set of PCI Express cores, and then on the side of the laptop have a bunch of M.2 NGFF bays, and let people pick what they want to put into modules. And that's the sort of thing that that particular market is actually really well suited to address. And they would find that, I think, a feature that they can completely configure the number of Ethernet ports and SATA ports and whatnot inside the laptop versus being told by some vendor that thou shalt have one Ethernet port or no Ethernet ports, right? And one of the interesting things is that in this market, it's a bunch of enthusiasts, and it's been shown that these guys drive margins and buzz. Like the overclockers and the gamers drive the high-end market for gigahertz and frames per second. I mean, you have like the Intel Extreme Editions and like those really super high-priced NVIDIA graphics cards that you can buy. And these people are single metric buyers, and they have a lot of money and they'll pay for anything. In a similar way, the Open Libre enthusiasts are pretty much single metric buyers. It's about transparency and freedom. They all tend to be fairly well-educated, fairly well-paid software developers, or they have foundations that can help them with this. And the interesting thing is they also have an overlap with system-level decision-making, and they're also the developers that you want to help develop, sort of code for your applications and tools. So it may be worthwhile. The point of this is it may be worthwhile to develop sort of a high-end, sort of compute-oriented ASIC, and dealing with this crowd. But the openness aspect has to be done right, or else you might get the opposite effect. You may actually get people pushing back against it and saying, this is not the open solution we're looking for, go back and try again. We're not going to buy this particular thing. So sort of just a recap of what I'm talking about when I talk about impedance matching is that the open hardware definition means different things to different users. Open hardware includes silicon level, system level, module level. People are putting open hardware licenses on craft, like sort of needlepoint and stuff like that. The thing is that open hardware, the user base is reasonably intelligent, but they're only partially educated on core issues, particularly relating to silicon. So there's going to be some effort that has to be required to bring people all up on the same page. The common values that they all seem to share is that open hardware should be hackable, should be free and transparent. But when you say there's no black boxes, you have to clarify it to what abstraction barrier. And so, as in electronics, as in real life, impedance matching requires finding a common ground. If you don't have a common ground, you can't impedance match, right? And we have to agree upon values and agree upon terminologies. And transparency, I think, is a really good on-ramp, possibly, for that. But you have to make sure you don't claim to eliminate all threats. You never can eliminate all threats. And instead, define your threat model, tell the people how you mitigate the threat, and let them make the assessment of what it does for them. But I think that open silicon represents such a unique advantage there. I think it should be a pretty easy argument. And of course, open hardware is still a minority market overall. I mean, the real economic strength, I think, behind RISC-V is not just an ideological argument, but the fact that you can just displace ARM cores and save royalties, right? That's going to drive, I think, a lot of adoption of RISC-V in itself. But you guys also need tool developers. You need people to go ahead and maintain your distributions and other things like that. And that's where sort of courting the open hardware, the open source community may have a derivative benefit beyond just the dollars, but actually may have a benefit in terms of forwarding the state of application software and tool chains for the RISC-V ecosystem. That's my talk. Thanks.
Hi, Megan Watts from Sci-Fi. Thanks a lot for the talk. Yep. So it sounds like for the open hardware, there's like open silicon. There's a lot of work to be done, and it seems like RISC-V is probably only one organization that might be in that space. Can you talk about other organizations that might be interested in open silicon?
Yeah, I mean, I think there's been a couple attempts at doing some open silicon. There's the Open 5 guys who are trying to do actually attacking the analog IP problem, which is interesting. And then there's the university groups that are working on it. But I think that just the idea of being able to do, I guess the problem, like before now, a lot of the attempts to do it were kind of more like toy attempts, and I think Chris actually had a really interesting sort of overview of some other people who had tried to, they tied the ISA too strongly to implementation. There's a lot of reasons why they couldn't actually grow into the ecosystem, because there's so many complicated issues in bringing this tape out to bear. And I think it's actually, the fact that, I think the sort of the inflection point was when, Sci-Fi brought the FE310 out, and you could just buy it as like a thing. It's not a test chip anymore, right? You can actually just buy it and start running code on it, which sort of shows the maturation of one ecosystem. And I hope that there'll be other ones that kind of grow around it, but as sort of like the furthest person who's furthest ahead, your back is also facing everyone else, and they're going to start shooting arrows at you. And so I think part of the point of the talk here was to sort of like get you ready for the sort of the scrutiny and the criticism that may be coming your way from the people who are trying to catch up to you.
You made it was a great talk, thought-provoking, but it seems hopeless. I mean that's the other conclusion you could draw from this, is that there's no way this is ever going to be economically viable.
In terms of?
There's going to be stuff that's not visible in this, on planet Earth. If you're getting a chip, there will be things that you can't look at.
Yeah, I think
that seems like a conclusion.
I think that when I was thinking about the list of recommendations that I came up with, the idea was to give you things that you can do things about now. There's a set of actionable things that we can do to mitigate sort of I would say in the next 5 years, I would agree with you. There's not a lot you can do. But what happens is that I think the founders are very risk averse, but they're also very margin challenged. And so you can't tell them that you're going to have more margins by participating in open ecosystem, have them believe it. You have to sort of bring them in. You have to lure them in step by step. So if you're to look at sort of the grand long-term plan, it would be like to sort of show that openness has a value and how transparency works, so that their salespeople kind of understand it, and try to tease out more and more blocks. And they're finding, why is this IP being like just all of a sudden ending up everywhere and everyone's coming to my fab? Oh, it's because like people can actually just design in my IP and they don't have to talk to someone and sign a license agreement and all that sort of stuff. All of a sudden their fabs are getting more business, right? So I think there is a path for them to sort of, particularly in older nodes that have, the equipment's been depreciated. I think you're trying to get like, 16 nanometer, 7 nanometer open from the get-go. There's no hope for that. But a lot of older nodes, you can fab out perfectly good chips, and the IP is well known, well studied, and it's just getting them off of their old practices. So I would say like on a 20-year arc or something like that, we may have totally open fabs where you can just share the GDS2 and have the kits available, and anyone can truly download and design, tape out, almost like a PCB fab, ship it out into pizza mask and some chips come back. I think that will happen. But the steps to get there, particularly by a leading community like this, is first to be like, look, how do we get, how do we explain to the open hardware community that it's going to take some time, right? We're working on this, and here's the intermediate step. And then once you sort of get to that point, you can sort of say, okay, we have a very popular trust route that's shipping, and if we could only just get the mask ROMs for this as GDS2, we would have a 100% inspectable thing. You can convince one fab to do that. Guess where all the orders for that are going to go, right? That one fab will get all the orders for that.
Okay, but your evidence that there was a market was Kickstarter, and you got almost $1 million of orders, right? That is not going to convince any commercial firm that we should go backwards in technology for openness, right? I mean, it's not. I think you have evidence that it isn't. Nobody would buy it.
Right.
There is a person to buy it, but semiconductor manufacturing's brilliance is they can manufacture hundreds of millions of chips, right?
Absolutely.
This is, is there a market that's 1% of the PC market?
Yeah.
I don't know. I don't know if there's one.
So I tried to address that issue head on. I didn't mean to say that the crowd supply that we did was meant to be a flagship thing. It was a hobby project, which we wanted to recover the tooling cost of, and we marketed it as that. We didn't even start a separate company for it, right? It's just like, in fact, we deliberately shuttered the project afterwards and didn't ramp up the hype because we knew there were more nodes of Moore's Law to come, and we were waiting for the right CPU to come along before we really do a full push on it, right? It was more of the idea is that it was testing price points and what people would pay. If we were to have something, would you pay $2,000 for something that just the main feature was openness? That's it. That's all you could say is that it's open. And the answer was yes. So it was more about price point validation and not market size validation. That's in the computing space. However, I will definitely say that
price point independent of market size.
Well, I think that there is a bunch of things we could have done to increase our market reach. Like we could have done a lot more PR, but I pulled back on it because I didn't want to make a company out of this. Like I actually was actively not trying to make this thing huge because I didn't want to just support an open hardware laptop for the rest of my life based on a bad note, right? And so, but not to get too distracted by the compute story, I do think there's a huge market for open trust roots, right? So the trust root silicon is a sort of thing that would go in key fobs, it would go inside every computer, it would go inside banking transactions, it would be used inside SIM cards, all these sorts of things. This is a millions and millions and millions market, right? I mean, this is an easy millions of markets. And the price points there have been confirmed to be actually quite high for irrational reasons, because there's only a few guys who managed to get some weird certification on black box stuff, right? So I don't think I need to make an argument that the people pay for it, and the people in that market have been clamoring for openness for a long time. But I haven't been able to push anything towards them, and I've had lots of people ask me questions about it because nothing's met my standard for what I would consider sufficiently transparent to build a trust root in. Now I look at these things and I'm like, no, you just can't. I can't make any. You've not moved the status quo any further because I can't confirm that MassROM is what MassROM is. Right? That just doesn't help me at all if that's your threat model at the end of the day. And I think that the actual cost delta in terms of the silicon itself to create these trust roots in the fashion we're talking about isn't huge, but the perceived value delta is quite large. And I think the market size there does get into millions and millions. And that's why I spent most of this, like 90% of the slides talking about sort of the trust root issue, and maybe like 2 slides at the end talking about the performance computing, more of an marketing exercise to try and get thought leaders and developers on board, and not so much as a way to recover the cost of fab at the end of the day.
Yeah, one of the things this seems to run into is that semiconductor manufacturing is inherently a mass production process, and the only way you can get away from that, if you give up enough, you can basically go back and build either in a really, really old process, in which case you give up all the performance and stuff that comes from anything modern, or you can go to discrete components and go far enough back, and then you're clean, right? But if you're trying to build something, anything like a modern process, you run into just the price of the masks alone is multiple million. Just building 1 million or so is just uneconomical. 1 million just isn't enough. And so then if you don't have those volumes, the only sensible thing to do is to do it all in FPGAs, which of course you can do, and that's a sort of much easier problem to solve. But I just think you run into semiconductor manufacturing economics. I mean, even today, we don't really know what the foundries are going to do once the mobile people come through and go from 16 nanometer to 10 to 7. Who's going to fill the fab after that?
Yeah, well, I think that's a very fair point, but I think there's a couple of interesting trends pushing against it. First of all, when I showed those earlier slides that says 28 nanometer, the last node of Moore's Law, whatever. At some point, like, the new fabs just stop being economical, and maybe the wafer price points don't ever even really become parity. So there's a point at which sort of what the cutting edge guys are, what's considered like minimum acceptable performance is actually also a 5-year-old or 10-year-old process. That's gonna play out in the coming decades, right? So that's leveling the playing field, right? The other thing is that, I mean, if I've already believed Jack and what he's telling me how much it would cost to tape out with Sci-5, it's not millions of dollars for a mask. He's saying like $100,000 or something like that. I haven't validated it myself. I haven't tried to place a purchase and do this. But if that's the case, that changes the equation. Like, I'm actually thinking, I'm talking with Sean right now. What in our canon of chips that we want to do, can we tape out at $100,000 and recover all costs in that versus what would pay a third-party vendor? In FPGA, the markup in FPGA is massive. I mean, we pay $20 to $50 in volume for an FPGA. If you reduce that to a $2 ASIC, you only need to sell 10,000 units to recover the tape-out cost, right? And that starts to get to the level of the kinds of things that we're doing in the open hardware community. We sell in thousands to tens of thousands, and it makes sense to do it. And so I feel like another thing that will also happen is I do feel there's about another order of magnitude eventually to drop on mask cost, particularly if you're willing to do like a 0.35 or 0.18 kind of node. And those aren't going to be super performing things, but keep in mind that there's a lot of Internet of Things, right, which run at 20 megahertz, that run at 50 megahertz. And really for them, it's about size, right? If you want to build something that fits in your ear, and you need the analog integration, and you need something that runs at 10 megahertz and does a little DSP, that sort of thing, your only option is do an ASIC at that point in time. But it may be fine to do it in an older node and just clock it really slow and have a lot of charge recovery or whatever methods you need to try and optimize power. But so I think that there are markets that will open up. They're smaller and more niche, and the mass cost will come down. But certainly, if we want to compete with an NVIDIA or Qualcomm or, Intel on a CPU basis, then yeah, we're going to have to be in cutting edge silicon, and it's going to be very expensive to do those masks.
So I have a question about if you believe in the conspiracy theory kind of thing, that if suppose there's some closed block of IP that's sitting on the chip and watching all the memory traffic as it's going by, and when it sees something interesting, it kind of just sends out a network packet to one of the 3-letter agencies or something. Then how do you build a trust a fence or whatever you called it to try to limit it from doing that kind of thing? Like, how do you put that kind of intelligence to protect against that kind of attack?
Yeah, it's called an introspection block. The idea is that there is a set of behaviors that a block is guaranteed to do and supposed to do, and if it does something outside of it, you flag it. So obviously, if you, for example, were only having one open block, which is your RISC-V core, and then everything else was closed source IP, you're kind of screwed because you have bus masters and targets that could initiate traffic independently. This is assuming that you have something closer to a situation where you're using an open RTL fabric, right? So that's all within your trust domain. and you're really now up at the edge of like a PCI Express block that has some hard PHYs, or a DDR block that has some hard PHYs, which you can't really get around because those are incredibly hard to design. And then the idea is that those should be fenced in pretty tightly in terms of what they're allowed to originate, what they can't. And so if something is from a PCI Express block and trying to write directly to your network interface on another thing, you would flag that with an introspection block. That would be the idea, at least.
Some of these, like the management engines, they're designed to send out and respond to network packets, and so that they would have some amount of functionality, and then so you'd have to try to figure out how do I distinguish between the expected network functionality versus this malicious network functionality, and that's kind of hard intelligence to bake in somehow.
The theory is that you wouldn't, if you're being open, you wouldn't have a closed source management engine on the inside. That's the root problem. If you built this open source chip and then you go ahead and gave someone like a management engine that they couldn't inspect, and they had to put that and reduce the attack surface on that, then that would defeat the point of the exercise. The idea is that if you had a management engine, that would also be open source as well. And you're just pushing the closed bits to the edge and with defined attack surfaces that you can then put portals on and monitors on. Of course, the more you expand your attack surface, the harder the exercise gets at the end of the day. I think it's, and like I said, I think the more realistic scenario is that you just have IP blocks that have native bugs or like test escapes or alias register banks that they didn't catch during verification, because verification guarantees that you work to the spec, but outside of spec, if you address outside of its address range, they don't care, right? And so register aliasing is a really popular exploit in the security domain. And so having like an assert block will take any sort of third-party IP that you can inspect and confirm they don't have register aliasing problems that would fall outside of memory protections that you might otherwise have, these types of things. And I think that would actually be the more realistic set of sort of issues you might, I think it's less likely that a three-letter agency goes and actually strong-arms Synopsys. It's more likely that the three-letter agency maybe hacked their network and has full access to Synopsys source code. And they know exactly where all the backdoors are. And then they construct a series of backdoors, which is like, okay, if I have this PCI Express IP with this USB IP and this Fabric IP, I can go ahead and flip these bits and then establish the network I need. Because the vendors already put those in there for you. You might as well just pull it out. You don't even have to tell anybody. You just sort of walk into the network, take the stuff, and analyze it, right? I think that would be the more realistic, vector.
So these introspection blocks you talk about, SoC vendors already put these things in, right? So if I have a PCIe interface on my SoC, I already put in an IOMMU, and it's because I have a commercial incentive to make my device secure. Basically, I don't want for there to be a commercially discoverable exploit where someone can attach an external PCIe device and recover all of my user's secret data. So I put in that IOMMU at the moment for that reason. Now, you're saying you want to expose that, prove that it's definitely there, and you're going to do that in Metal 3? I don't really understand how that works, because obviously from Metal 3 down, I can change a lot of stuff.
Yeah. So first of all, the point about the IOMMU is very valid taken, but there is a known published exploit, I'm pretty sure it's published, on the PS4. The way they got in was through the IOMMU. It's literally reprogramming the IOMMU from the device side. And you had to just get to the TLP layer, and they assumed some abstractions wouldn't be broken, and they managed to walk past the IOMMU and go into ring zero space as a result of it, right? So part of the problem is that the IOMMU is an opaque block you got from somebody, and they're guaranteeing it does its thing, and they may not be spec compliant. And so the idea is that you can have a whole team of people review the RTL who are very security minded, right? And so so the idea is the introspection blocks would be peer reviewed, group reviewed things that we would then improve and have exploit sort of CVEs and sort of stuff to sort of improve that from the standpoint of making sure there aren't exploits like that. So that's one thing. So the reason why you want the introspection blocks is not that they don't have measures like this already, it's that all those measures are closed source. And the closed source stuff can still have bugs, and the closed source can still have backdoors. So you want to have an open source version of an IOMMU that you can place anywhere and sort of like fence something in. It'd be a general purpose block. And what I'm saying sort of from the inspectability side, this is, ideally we would have, of course, transistor level mask patterns, but talking to people, I think that might be really hard to get, particularly in cutting edge process, that sort of stuff out. And it's also really hard, from personal experience, imaging anything at that level. Really sort of M3, M2 is where the limit of easy imaging happens these days, at least in the nodes that I've looked at. And so the question in my mind, the proposal is more like a thought experiment. Like, given that M3 is about our visibility, can we come up with a set of RTL techniques, compilation techniques, and design techniques that, assuming that you do, full mask edit on M2 and below, within the density of the core and whatnot, can we limit the amount of damage someone can do to my introspection block, in particular, in terms of what it can do? So, for example, if you want to go ahead and swap out you're doing a tap on a hardcore ROM, and you want to swap out a whole set of code with a mux, and so you don't see it in one mode, but a magic code comes and you see another one, and you had to hide that from M2 and below, that's going to be hard, right? You're not going to have enough spare cells, and you're not going to have performance necessary to be able to do that. Or if they did, you would start to see some weird stuff happening in M3 that you wouldn't expect going on. And the idea would be to try to design, those particular blocks as inspectable blocks that you make it harder for someone to do an exploit. That you just pack in the gates into one region. You don't really have a lot of spare cells. It's it's in a defined region by itself, so you don't have a lot of overlapping metal, whatever it is. You kind of solve it, kind of meet in the middle, and say like, look, M3 and above, not an absolute guarantee, but a way better guarantee than you've ever seen before, and probably the best you'll get in any cutting edge process. That's the gist of it. Of course, it's half baked.
Yeah, I mean, maybe I could talk to you afterwards. I think it may be kind of theoretically possible to create a design where modifications below M3 will not affect the behavior of the circuit.
Yeah,
But
sure.
and is that formally provable? That's the sort of
That's the question I have, is can we create like some sort of logic form so you can formally prove that there's no way that a swap of a gate within a certain parameter space can cause a collapse of the logic function. This is this is a thing that I'm not personally good at, but it's the sort of problem I can pose at least to somebody and say, can you think about this for a while, come up with some papers and some exploits, and let's talk about it. But in terms of like, this is the best thing, instead of saying just throw it in my hands, like, nope, we just can't verify anything, right? That's the other option, is that we can't. Or the other option is say, like, we're not going to get anywhere until we have the fab release, like, the design of the transistors. That I also don't think that that's going to be a fast fight either at the end of the day.
This is Jack from SciFi. So there's a lot of reasons or benefits from being open, from the software side, and you kind of talked about it in the why open source hardware is like for inspection purposes, or for people to build things on top of them, or to leverage prior work to build more things, which I think software had a major benefit of. Now each of those is probably a very difficult task for hardware to get to, but if you were to kind of prioritize, like say, hey, well, we should really try to solve this inspection problem first, or we're really trying to get the ability for people to reuse stuff first, or the really ability for people to study stuff first, right? Because each one have related but kind of different challenges. So like, from your community, what's more important?
Again, you're the marketing guy. So the question is where do you think your market is at the end of the day? And that's where. And then if you said we wanted to go for trust roots, and we think we have defensible ground there, then I'll be like, yeah, you definitely need to have introspection and that sort of stuff. If we want to say our market is actually just reducing the cost of masks and kicking ARM IP out, then you don't need introspection blocks. That's the argument's been made already, I think, over and over again, right? And so. You have your business to run. I'm not going to tell you how to run it, but I like the idea of inspectability and transparency coming from sort of an unaffiliated, free agent, open hardware. I like to trust what I'm running, sort of thing. I already, probably have like a dozen rootkits running on my phone right now because I'm in China or whatever it is, right? And so it's like, I would like to have something I can use to solve these problems that I have. With trustability, but that's a me. I'm very aware that's a me issue, and there's a small other group of people. But that if you can find a solution to that problem, then it's very I think you have a much bigger market of like banks and financials and just everyday login credentials and trustability that can be solved by it, and you can create a very high bar that'd be very difficult for anyone to cross.
I think that makes sense. I think just kind of my comment is I think as a hardware community, I would probably view these as independent type problems. So I think there's different areas that can benefit from Like let's say, okay, we can solve the inspection problem, but we can't solve the, it's really easy for somebody to then take that and modify it and build something else, right? I think in a way, these are like separate lanes where we can solve them. Don't let one hold you back from the other, I guess is kind of what I'm saying. So I think there's different markets where we can use.
Yeah, I mean, I think there are people who could develop the RTL for the introspection stuff, separate from everything else. The mass inspection stuff is it's more of a proposal. Like it's like an idea, maybe a way forward. But I think if you just even got to the point of an introspection engine with an RTL solution, and you had all of your other wonderful stuff going on, that was a separate working group, that would be progress, and you could point to that.